is. So we're in section 5.4. So a median of a triangle. Is the segment that goes from a vertex. I'm going to go from a vertex to the midpoint of the opposite side. So if we draw a triangle here, a median is going to go from a vertex to the middle of the opposite side. And the way we know it, we're in the middle, we get two congruent segments on either side of the midpoint. So that blue segment would be a median. So our theorem. Everybody good with what a median is? Our theorem is that the medians of a triangle are concurrent. And remember, concurrent means they all intersect in one point at a point called the centroid. And I'll write down in just a second what is special, several things special about a centroid, but let me draw a picture here. So here's my triangle. I'm going to draw all three medians. Kind of So what the theorem tells us is all three medians are going to meet at a point. And we know that we have medians because the medians go to the midpoint of the sides of a triangle. And I'm going to call that point P. And P is the median. Or sorry, the centroid. The centroid is 2/3 of the distance from the vertex to the opposite side. So what we're saying here is if we look at this median along this, going along this median, it's saying that this distance is 2/3 of the way across, and this distance is 1/3 of the way across. And that's true on any median. This is 2/3 of the way, that's 1/3 of the way. 2/3 of the way, 1/3 of the way. So the median, or the centroid, is 2/3 of the way across the triangle. The other thing that's special about the centroid is if I drew this triangle out on a piece of cardboard and I found the centroid is where that cardboard triangle would balance perfectly on the tip of a pencil. So it's the center of mass, the center of gravity, the balance point. So the centroid is 2/3 of the way across the triangle. It's also the balance point of the triangle. Centroids of other shapes are quite a bit more complicated to find. Triangles are nice. The centroid is always inside the triangle. The balance point of a triangle couldn't be outside of the triangle. So it's always inside. All right, so I want to look at an example that has to do with a centroid, and then we'll talk about altitudes. So here's my triangle. And I'm going to label this S, L, R, M, T, and N. All right, so before I ask the question, based on that drawing, and I'll call this point P, what is point P? It's a point of concurrency. We have three lines coming together there. But we've talked about several points of concurrency. So what is that one? That one's going to be our centroid, because we're going from the middle of one side to the opposite vertex. So P is the centroid. So that's going to be probably going to be important information here. And I'm going to say that SP is 16, and we want to know what SM is. So SP is this, and SM is this whole length here. Well, SP is from the vertex to the centroid, and we know how much of the triangle is that across? 2/3. From the vertex to the centroid is 2/3. So I'm going to say we know that this is 16. That's 2/3. This is 1/3. So SP is 2/3 of the total distance, SM. Well, SP is 16. It's 2/3 of SM. So to figure out SM, I can multiply both sides by 3 to get rid of that 3 in the denominator. 3 times 16 is 48, and that's twice SM. Then I can divide by 2. And I get that SM is 24. What's 1/3 of 24? What is it? 8. So that this distance would be 8. Is 8 plus 16 24? Yeah. So 1/3 of the distance, 8, 2/3, 16. The whole distance, 24. So the kinds of problems that you'll see that have to do with centroids often have to do with the distances across the triangle. That 2/3, 1/3 thing. All right, questions there? Now, before we go on, I just want to, it's kind of, there's no really no reason to expect, just thinking about it, that the median would all intersect at one point in a triangle. So it's kind of a cool thing that they do. All right, next idea is an altitude. And we've talked about this a little bit before. We usually call the altitude the height of the triangle. Technically, the altitude is the segment, the height is the length of the segment. But the altitude or the height of the triangle is a perpendicular segment from a vertex to the opposite side. And I'm going to put in parentheses, or an extension. And what I mean is, if we have an obtuse triangle, we'll draw, let me draw some triangles here. If we have a nice acute triangle, our height is just this blue segment here. We go from a vertex perpendicular to the opposite side. If we have a right triangle, then a side of the triangle is the altitude. So both of those would be altitudes. This is from a vertex perpendicular to the opposite side, vertex perpendicular to the opposite side. But if we have an obtuse triangle, we have to find, depending on which side we use, we have to find the altitude outside the triangle. So I would need to extend this side to get my altitude. So I can make a 90-degree angle. So we have to extend the side to get my perpendicular segment. So for an obtuse triangle, the altitude's outside. All right, so our theorem. Our theorem for the altitudes is that the altitudes are concurrent. At a point called the orthocenter. So again, there's no real reason to expect that all three of the altitudes would meet at one point, but they do. Now there's not a circle, or there's nothing other than the fact that all the altitudes meet there. There's no additional information about the orthocenter that's special. All the altitudes meet at a point called the orthocenter. The altitude, or the orthocenter, can be in, on, or outside the triangle. So let's draw those cases. So it can be, if we have an acute triangle, our orthocenter is in. So I'm going to draw 3 altitudes here. And those are perpendicular segments. So it can be in an acute triangle. It can be on a right triangle. So for this right triangle, here's one altitude, perpendicular segment from a vertex to the opposite side. Here's another altitude. Will they meet here? If I drew in the third altitude, it would go from this side right there to that vertex. So On a right triangle, the orthocenter is at the vertex by the 90-degree angle. And for an obtuse triangle, because we have to extend the sides, for an obtuse triangle, our orthocenter is outside the triangle. So let me draw my extended sides. I have to extend that side, and I have to extend that side. And I need to make that a little longer. And I need to extend that one a little more. So this one would need to come out here. So there would be my orthocenter. There's my perpendicular segment to the extension. So the orthocenter would be here. And if I drew the perpendicular segment from this side, it would go like so. So it's outside an obtuse triangle. And my triangle here is, I'll do that in red. That's my triangle. So the orthocenter is outside the triangle. And it turns out that the orthocenter, the centroid, and the circumcenter, all three of those points, if we drew them for any particular triangle, all three of those points end up on the same line, which is pretty surprising. Three random points generally don't end up on the same line. But those 3 points are on the same line. All right, so I want to look at just one more example, and then I'll summarize our points of concurrency. So for this one, we want to decide if these points are medians or altitudes, or these segments are medians or altitudes. So here's my triangle. I'm going to draw my segments in blue. All right, so the question is altitude, median, or neither. How about segment AC? So this blue segment here. Altitude, median, or neither? What is it? Someone said it. Median, right? Goes from the midpoint to the vertex, the other side. AC is a median. How about segment AD? This segment. Median, altitude, or neither? Neither? What is that one? It's just a side. And it's not a right triangle, so the side can't be an altitude. How about segment AE? This blue segment. That's an altitude. It goes from a vertex perpendicular to an extension of the opposite side. Can we think of a type of triangle, so we're not talking about this one anymore, a type of triangle where the altitude, the median, the perpendicular bisector, and the angle bisector would all be the same segment? Anyone want to take a guess? How about an isosceles triangle? So if we have a triangle with two sides the same, like so. Didn't we say that if we bisected this vertex angle, that segment was the perpendicular bisector of the base? So this is an angle bisector, perpendicular bisector. This is the midpoint of that side to the opposite vertex. So that's a median. And it's also from a vertex perpendicular to the opposite side. It's also an altitude. So this, in an isosceles triangle, that segment from the vertex angle to the middle of the opposite side is all four of those things: altitude, median, perpendicular bisector, angle bisector. Could we think of a triangle where all three, if we do those things to all three of the sides, that all three of the segments that we draw are angle bisectors, perpendicular bisectors, medians, and altitudes? About an equilateral triangle. For an equilateral triangle, we have two sides the same. That happens. That's true on any vertex. So on an equilateral triangle, every segment that we draw that's an altitude, a median, a perpendicular bisector, or angle bisector is all four of those things. So a couple special cases there. All right, let's summarize our points of concurrency in a triangle. So yesterday we talked about the in-center. And which segments intersect in the triangle, which segments give us the in-center. The in-center is the same distance from the sides of the triangle. Which ones? That would be the circumcenter. So look back at your notes. Which segments intersect to give us the in-center? Angle bisector. And we also had the circumcenter. Those are the ones we talked about yesterday. This is the one we did our constructions for on the board before class. The circumcenter is the perpendicular bisectors. Today we talked about the centroid and what intersected to give us the centroid. The which ones? Medians. And then we talked about the orthocenter. And the orthocenter came from the altitudes. The in-center and the centroid are always inside. And the circumcenter and the orthocenter could be in, on, or outside. Acute angles, acute triangles, right triangles, and obtuse triangles. Some people come up with mnemonics to help them remember which ones give which things. I always just remember how they, with the incenter and the circumcenter, which ones are the same distance from the sides or the vertices, and the centroids. And centroids show up in other contexts, so I remember that. So you can come up with some way to remember how all of these things work. All right, our homework.